So welcome back. This is our lecture number 13, and now we're going to discuss the belief propagation algorithm. So we know that in general, inference in networks is an NP hard problem. So it means that some networks will have a large tree width, and for those networks, it will be very difficult to provide exact answers to our queries in a feasible amount of time. So we can think that is it possible to find algorithms that instead of providing exact answers to our queries, they will provide some approximated answers, but they will require much less time to compute those answers. So we need to find algorithms that are at the same time able to provide good approximations. So if we compute the difference, the distance between the probabilities that are being provided and the true probabilities, the distance will be small. And at the same time, the complexity of those algorithms will not be exponential in the tree width of the graph. So it's interesting that the belief propagation is a good candidate for those algorithms, because it's not just one algorithm, it's actually a class of algorithms that range from, in one side, very efficient but highly approximated algorithms, and the other side, they can provide exact answers but will require much more time for computing those answers. And you're going to see that the joint tree algorithm that we discussed 2 lectures ago is going to be one member of this belief propagation class. So let's get started and see how those algorithms work. The classical belief propagation algorithm was the first exact inference algorithm proposed for Bayesian networks. It was in the beginning of the 80s, and it made an assumption that the network had a polytree structure. So just remember, a polytree structure means that we have no loops. Therefore, the tree width of those polytree networks will be fully determined by the maximum number of parents that we have in a single node. So it's interesting because we cannot expect a network that has a simpler structure, because the tree width will not depend on loops, and the maximum number of parents that we have in a single node we can somewhat control by making independence assumption. Later on, in one of his books, Julia Pearl making one observation that we could apply this belief propagation algorithm that was defined for polytrees in networks that have loops. In this case, the answer will not be exact, but it could be of a high quality for certain cases. And it was just one paragraph in the book, and actually no one paid much attention to those methods until the turbo codes were proposed. And it's an interesting story, because the turbo codes were proposed by an independent group of researchers and practitioners that were working with computer networks. So the idea of the turbo codes is to have an error correcting code. It's basically we take one message expressed in bits and we add some more bits, and those bits can be used to detect when we have a transmission errors, and also in sometimes in fixing those errors and recovering the original message. And those turbo codes became an industry standard, and now it is used in several types of networks, including the 3G and the 4G networks. So those turbo codes can be understood as a Bayesian network, and the inference algorithm behind those networks is this belief propagation algorithm. So it's interesting to know that we do have in our smartphones a small piece of code running a Bayesian network with those belief propagation algorithms. And this has sparked a new area of research in Bayesian networks, in which the researchers started looking for what was the meaning of the belief propagation in loopy networks, as well as when those algorithms could provide some good approximated results. So we're going to see in this lecture that this approach can provide us a full spectrum of approximations. So in one side, we have the belief propagation algorithm that is highly efficient, but it's also very simple and cannot provide good approximations in some cases. And in the other side of the spectrum, we have more complex algorithms that required more time to compute the answers, but they can provide some exact results. And you're going to see that the joint tree algorithm that we discussed 2 lectures ago is actually one representative of this class of algorithms where we can provide exact results. So let's get started by discussing the classic belief propagation algorithm. First, it is a message passing algorithm. So as we have seen before, we're going to have a structure where we send a message between the nodes, and those nodes will take this message and multiply by the factors stored in the nodes. But this algorithm is specific for one class of Bayesian networks that are called the networks with a polytree structure. So the polytree structure means that we have only one undirected path between 2 nodes. If we look here in this example, we can confirm that, right? So if we take 2 nodes like A and C, there is only one path connecting them. If you take like A and E, there is only one path connected them. And if you look at A and F, for instance, we have only one path. But the fact that we have only one path, we cannot have loops, right? Because if we had a loop, like a connection between these 2 nodes here, we could have like 2 paths going, for instance, one this way and another one this way. So this restriction of polytrees of having just one indirect path between 2 nodes basically means that the structure has no loops. And since the structure has no loops, and we know that the tree width of a network is influenced by 2 factors. One is the presence and number of loops, and the second one is the number of parents that we have in a single node. So in this case, the tree width will be controlled by the number of parents that we have in each node. So if the maximum number of parents in a network, in a polytree network, is k, so we know that the tree width will also be k. And in this case of this network here, it's a polytree, so we know that the tree width of this network is actually very simple to compute, and the tree width here is going to be equal to, because the maximum number of parents that we have is 2, and it is B and C for node D. So let's take a look at how we're going to compute the messages and the answers for this belief propagation algorithm, and those answers will be exact, and we'll see how we can extrapolate this algorithm to networks with loops later on. So when we have a polytree, we can construct a joint tree that is optimal for that polytree. I mean by that if you have a polytree with width W, we can construct a joint tree for this polytree with the same width W. And the procedure is actually very simple to do. So we have here one example of a polytree, and we know that we have factors here that express the probability of A here on the top. Here we have the probability of B given A. Here we have the probability of C. Here we have the probability of D given B and C. Here we have the probability of E given D. And here we have the probability of F given D. So in order to construct the joint tree, what we do is to create one node for each node that we have in the polytree, and one connection, one edge between the nodes for each edge that we have in the polytree. So we need to define what are going to be the clusters for this joint tree and also the separators. And the idea is simple. The cluster here for this node is going to be over the variable A, because we're going to associate this factor, the probability of A here. For here, we have a cluster mentioned B and C, A and B, sorry, because we have this factor here that's going to be expressed here. Here, we're going to only mention C in this cluster because we're going to associate this factor with the probability of C here. Here, we're going to have B, C, and D because this factor will be stored here. Here, we're going to have D and E because this factor is going to be associated here, and DF because of this factor here. Right? And in order to compute the separators, what we do is to check for the intersections between 2 pairs of clusters that are connected with an edge. So here we have A and AB, so this separator is going to be A. Here we have AB and BCD, so this separator is going to be B. Here we have a C and BCD, again, we're going to separate to C. DE and BCD going to be D, the separator, and DF and BCD, the separator is going to be D. So we can easily see a pattern here, right? So let me just erase this guy here, otherwise it's going to be too messy. And so what is the pattern? The idea is that for each node we have the variable in the associated node in the base network plus the parent. So here we have A, and we don't have a parent, so A is going to be alone in this cluster. Here we have A and B because we have this guy here, that B, plus its parent, that is A. Here we have C because C has no parent. Here we have BCD, that is D plus its two parents B and C. Here we have D and E because we have E and its parent D, and here we have DF because we have F plus its parent D. And we can also see that there is another pattern for the separator, and the separator is the parent variable for each node. So here for the node B, we have the parent A. Here for the node D, we have the parents B and C, and here for the node E, we have the parent D, and for the node F here we have the parent D. So two important observations here is that joint tree width is equal to the poly tree width. So that is occurring because the largest node that we can create is determined by the largest factor that we have in the poly tree, and each joint tree message is going to be over a single variable. So we can see that the separators here are single variables. They are basically they are the parent variable for each node. And the fact that we have so small separators, it means that our messages will be really efficient, right? So we're going to send a message over a single variable, so they will require very small amount of memory to be stored, and they're going to be very efficient to compute. At the same time, our largest cluster has the same size of the largest factor that we have in the base network. So we cannot expect anything better than this joint tree. Okay, and the belief propagation algorithm is a message passing algorithm. It means that we need to choose one route, send the message toward the route, and accumulate the message and compute the marginals. So in this case here, you're going to use the same notation as in the book. That is the original notation used in the paper that proposed the belief propagation algorithm. And I have to say that I don't like this notation very much because this message will differentiate between the messages that are coming from the top of the network towards the bottom of the network from the messages that are coming from the bottom to the top. And there is no reason to make this differentiation because the message will be determined by the same equations, right? So we could simplify the notation by using the same symbols to the messages that are coming down to and the messages that are going up. But the book made that decision to include this notation, and even the author of the book, he said in one of his lectures that it was a difficult decision. I think that the main reason for adopting this notation is because it is used in several papers that mention the belief propagation algorithm. So there are these two types of messages. A message that is from a node U to a child X, we denote by pi x U, and it's called the causal support. And there is also a message from a node Y to its parent X that we call the lambda Y and X in parentheses, and this is also called the diagnostic support. So basically we have here the figure. Let's suppose that we chose this cluster here, BCD, to be the root. So we're going to send a message towards the root. So the idea is that we can start with nodes that are peripheral, like A here, or DE here, or DF here, because these nodes, we don't need to wait for any other message to start sending them. It's going to be different from AB here. If you want to send this message here from AB to BCD, we have to wait for this message here, right? So, but in the case of A, we can send the first message right away. So something that we can note in this notation is that whatever we have here between the parentheses is going to be the separator. So we have A here, we have B here, C here, and D, and have D and D, right? Something that I don't like here is that the subscript have different meanings. So in the case of the pi messages, B here is the destination, right? So we are sending this here was the old B node that we have in the base network. So again, D, we're going to send this message towards D. But when we are talking about the lambda messages, the subscript here is actually meaning where the message is coming from. So it's coming from the old node here that was the node E in the base network, and here was the node F. So it's a little bit to memorize this notation. Anyway, if you want to compute what's going to be the belief of this node here, right? So they're going to be a factor. What we have to do is the same thing that we had before with the join tree algorithm. What I'm going to have is first a multiplication of here the factor that is stored in this cluster, right? And also the multiplication of the message that are coming from the parent and the message that are coming from the child, right? So we're going to have the factor that we have here in the node BCD times these two messages here, this message and this message here, and times whatever comes from the children, these two messages here, one here, and one here. So when we multiply this everything together, we have this marginal, and we can answer queries regarding the variables B, C, and D. So in the case that we have evidence, what we do is exactly what we did before with the join tree. So just to be clear again, this algorithm is not a new algorithm. Even though we are using a different notation, it is the join tree algorithm that we saw before. The only difference here is that we are not working with general networks. We are working with one specific network that has this join tree structure. So in this case, we can easily compute a join tree that is optimal, that has the same width as the tree width of the polytree. So in the case that we have evidence, what we do, the same technique that we did before. We have the evidence indicators. We make these evidence indicators, they are factors, they are compatible with the evidence. So it's going to associate one in the case that for the entries that are consistent with the evidence, and we're going to multiply those evidence indicators to the factors respecting the variable, right? So for instance, if we have an evidence indicator that mentions the variable A, we're going to create this lambda A here, and we're going to associate it with this node. So we're going to multiply by the factor that we have there, that is the probability of A. If we have an evidence that mentions variable B, so I'm going to create an evidence indicator, and we're going to be multiplied here, and so on. So at the end, what we have is going to be this equation here to compute the marginal, right? So we have the evidence indicator that is compatible with the variables that we have in this cluster, times the factor that we have in the cluster, times the messages that are coming from the parent nodes, times the messages that are coming from the child nodes. And that's all. So now let's take a look at how we can compute the messages. So we have these two classes of messages. Actually, they are the same message, the same idea of sending a message between two nodes, but now we're going to differentiate between the messages that are coming down to the messages that are going up. So let's suppose that we have a node X, and we need to compute a message that goes from X to one of its parent. So this is going to be one of these lambda messages here, right? So they are going up. So this message will have the following components. First, you're going to have the evidence indicator, if we have one, associated with the node X. Unfortunately, now we are using the same letter, lambda, to indicate the evidence indicator and also the message that are going up. But yeah, that is because we haven't been using lambda for evidence indicators, but keep in mind that these are two different things. One is a message, and the other one is a factor that indicates the evidence. So here we have the factor associated with node X. Here we have all the messages coming from the older parent, but UI. So we send a message here to UI. We don't need the message coming from the UI. That's very important. And we also need the message that are coming from the children. So all the children must send its message. So it's very interesting that in order to X send a node to one of its parents, we need to wait for all those messages. All messages coming from the children and also all the messages coming from the older parents. And we multiply everything together and we eliminate the variables that are not in the separator. So in this case here, we're going to eliminate all variables but one, that is the variable UI. And that is basically what is being expressed in this equation. Just to mention that once again, that is very important. The message that goes from X to UI does not include the message that came from the UI to X. So take a look here that in the multiplication, we are multiplying all the messages from all parents, but the message that came from the UI. So we are excluding the I here, right? So I take all those messages, but I do not take the message coming down here. So remember that is a very important part of the implementation of this algorithm. So this is another figure now for the causal messages. So the causal messages I mentioned that are going down. So I send a message from X to one of its child, that's YJ. So in order to compute this message, I need all the messages coming from all the parents, include UI, right? And all the messages coming from the children, all the children but YJ. So let's take a look at here in the equation. We have the evidence indicator, we have the factor that is associated with X, we have all the messages coming from the parents, and we have all the message coming from the children but the message that came from YJ. And we multiply everything together, we eliminate all the variables that we have in the parents, so the message will be over X, and we send this message to YJ. So again, I know that I'm being repetitive, but look the same pattern. In order to compute this message going down here, I do not include the message that came from YJ to X. So it's interesting to note that some nodes can send messages right away, and these are the nodes in the top of the join tree and the bottom of the join tree. So for instance, if I have one node X here that has one single parent, it can start by send the message to its parent right away. And if you have one root node, when I say root here, I'm talking about the roots of the polytree networks. This root node can send the message to its child right away. So in this case here, the message is going to be slightly simpler because they will not involve other messages. So in this case of send a message up from X to its parent, this message will only involve the evidence indicator and the factor in the node, and we're going to eliminate the variable X. For a message that's going from the top, from the root node to a node that is its child, it's going to be one of these pi messages here, only involve the evidence indicator and also the factor, and I don't need to eliminate any variables in this case. So we have one example here. Always good to look at one numerical example in order to check our understanding. So we have here a polytree with its nodes, structure, and also the parameters, right? So here we have a join tree for this polytree, and we are illustrating the messages that are going towards the node BCD. So we selected this root of the join tree, and we're going to send the message towards this node. In a later step, we will also have to send the message from BCD to all the other nodes. So we're going to have the message in the two directions, and from there we can compute the marginals for each cluster, And in this case here, we can answer queries regarding A. Here we can answer queries regarding the variables A and B. Here C, and so on. So what's going to happen here? So the nodes can start and send messages are the nodes A, the node with the cluster DE, and this node associated with the cluster DF. The message will be slightly different. The ones that are coming from the top to bottom will not involve any elimination, but the ones that are coming from DE and DF will need to eliminate the variables E and F. So take a look here that we have this message here, pi b a, that has the separator A, and we have this factor. So originally we have this factor here, and we need to compute this message. But as this factor mentions variable A, and the separator is also A, so I don't have to eliminate any variable. So I just send a message that equal to this factor here. Okay? For the messages in the bottom here, we will need to make a little bit of inference, because we have to eliminate the variables in the nodes. So just forgetting to mention that we do have evidence here that's E equal true. So if I have the evidence E equal true, I will put one evidence indicator in this node here, right? That is gonna eliminate in practice. We are going to eliminate the entries that do not match the evidence. So we're going to eliminate these two entries here. So the indicator would be lambda here, lambda E. And in fact, it will not eliminate the rows, but it's going to turn those rows equal 0. But to simplify, let's just think that we are eliminating those rows. So the message that comes from this cluster here, the E, and goes to the cluster BCD will be based on this factor here and the elimination of the variable E. So we're going to remove this variable E here. So at the end, we have this message that only mentions the variable D and has 0.9 and a 0.3. On the other side here, we have the message that is this guy here. It comes from the node with cluster DF to BCD. In this case, this message will be based on this guy here with the elimination of the variable F. So we're going to eliminate the variable F here. I'm going to sum over the values of F. So we have one value here for D true and another value here for D false. We're going to sum to 1, 1, and we send this message up here, right? So these are the three initial messages. Again, we have these two messages. Oh, we have this message here that also do not depend on anyone. So I'm going to be based on this table here. Again, the separator here is C. So we don't need to eliminate any variable, so it's just going to be a copy of this factor here. Right? So these are the three initial messages. We don't have to wait for anything, but this message here will need to wait for this message pi b of A. So to compute this message, what we have to do, we have to take this message here and multiply by this factor here. So we do the multiplication and eliminate the variable A here because the separator is B. So after we multiply and eliminate A, we have, as a result, we have this message over B only with these values here. And they're going to be sent to this node. Now, this node here in the middle can compute the marginal. And the marginal will be the result of the following. We're going to take the factor that is associated with this cluster. That is this factor here. We're going to multiply by this message. We're going to multiply by this message. We're going to multiply by this message and by this message. This message here will not be involved because it's not one of the message that one send it directly to this middle cluster here with BCD. It will be incorporated indirectly in this message that is coming from the cluster AB towards the cluster BCD. And if we multiply these together, we get, as a result, we have this marginal here. And we can use this marginal to answer queries that involve the variables B, C, and D together with the evidence E equal true. So once we have computed this marginal, we can answer the queries I was saying before. So one possibility is to answer this query here, probability of C and the evidence E. And in this case, we have to eliminate the other variable. So we created this marginal here, and we need to eliminate the variables B and D in order to compute this. And if we do that, we get this as a response. In the case that we are interested in the probability of C given E, we have to do another step. There is the normalization of this factor here. All right, so we can also answer queries regarding the variable C if we, for instance, look at this node here. So when this node gets its message from this cluster BCD, we can multiply by the factor that we have there, and we can also answer questions regarding the variable C. In this case, the answer is going to be exactly the same, right? Because this is an exact method, so we're going to get the same results that we get from the elimination of variables B and D from this large marginal here. So just to be complete, we can use these equations here. The difference between these equations and the previous ones is that we are introducing this neta here as a constant. So we are basically saying that we can renormalize these messages and also these marginals here in order that they will sum to 1. And this is a very common practice, and it will help to avoid the case that we have underflow. So for large networks, we will be multiplying messages by factors and again by other messages and send these to other nodes. So it will be a sequence of multiplications of numbers between 0 and 1s, and this will make the numbers smaller and smaller, and we may cause underflow in this case. So this notation here is saying that we can compute a message, renormalize, and send the message, and this message will be multiplied by a factor that we can later on renormalize and compute other messages and keep in doing. So we don't let the probabilities to get too small because we keep renormalizing these factors, and that will avoid underflow. So this is a very common technique, and I'm going to see this neta if you look at other papers and other books. It's a sort of a standard technique for that. Okay, I think that is good for this first video, and let's continue in the next one by applying these same equations to a network that has loops. All right, see you soon.